All right, hello everyone. Today we are starting off our video with 7.3, which is on the reaction quotient and equilibrium constant. The reaction quotient, which is labeled as Q, tells us the relative amounts of reactants and products at any moment, not just at equilibrium. It uses the same expression as the equilibrium constant, but the values may not yet represent equilibrium conditions. And so what we can do is then compare Q and K and predict the direction that the reaction will shift in order to reach equilibrium. So if Q is less than K, then the reaction is going to proceed forward to make more products. If Q is greater than K, then the reaction is going to shift in reverse to make more reactants. And then when Q equals K, the system is going to be at equilibrium. And just like equilibrium expressions, pure solids and liquids are not going to be included because their concentrations do not change. Last lesson we learned about K, which is the equilibrium constant, and today we are introducing Q, which is the reaction quotient. Now, both of these use the same mathematical expression, as you can see here, but they're going to describe the reaction at different times. So K are only going to use concentrations or pressures at equilibrium. If they are not at equilibrium, then most likely you are using them to solve for Q. Because the reaction quotient uses concentrations or pressures at any moment, we can go ahead and use Q to relate it to K, and that's going to help us predict the direction that the reaction will shift to reach equilibrium. So if Q is equal to K, that means we are at equilibrium. If Q is less than K, then we know the reaction is going to shift to the right to make more products. And then if Q is greater than K, then it's going to shift left to make more reactants. All right, so let's use some make-believe equilibrium constants so we can make sure we understand this concept. So looking at Q equals K, we know our K value is equal to 4.2 times 10 to the third. That's going to tell me that at equilibrium, I have reactants and products, but I do have more products than reactants. That is where my equilibrium lies. Now when Q equals K, those constants are exactly the same. So we have the same amount of products versus reactants, and the rate of the forward reaction is equal to the rate of the reverse reaction. Now what happens when Q is greater than K? If I solve for Q and I get 9.8 times 10 to the 7th, I know that my Q value is much higher than my K value. So since I know that equilibrium is at 4.2 times 10 to the third, and right now with this information I'm given, I have 9.8 times 10 to the 7th, that means I have way too many products compared to that of my equilibrium. So that means in order to get to my equilibrium, the reaction is going to shift left towards the product side. Now looking at the Q is less than K, if I solve for Q and I get 1.1 times 10 to the negative 10th, I know that that is much farther on the reactant side than my equilibrium of 4.2 times 10 to the third. So I know that I need to shift to the right to make more products. And just a reminder with our equilibrium constant expressions, when we have Kc, or in this case Qc, the expression is going to look mathematically the same. They're going to use brackets to show concentration or molarity, and they are going to be raised to the power of their coefficient. And remember, it's always products over reactants. And same with QP or KP, except they're going to use partial pressure units, which is what the capital P is for, and they are in parentheses as well. And we are still going to be raised to the power of the coefficient. And it's also still products over reactants. All right, so if we were given this reaction on the left and it asked us to write the equilibrium expression, we would write K, And it did not tell me whether to do Kc or Kp, so I'm going to go ahead and look at the states of matter. Because I have aqueous solutions, I'm going to assume we are solving for Kc. So remember, when we are solving for Kc, it is products over reactants in brackets to represent molarity, and then raised to the coefficient. So first, our first product is Cu plus, and it is raised to the second power. And then we have Pb4 plus, not raised because it has a coefficient of 1. Then we have Cu2 plus squared, and then we have Pb2 plus. Now the cool thing is if you are solving for Q, which means you are given a bunch of concentrations but they were not at equilibrium, then it's the exact same expression, you're just setting it equal to Qc instead of Kc. And now let's go ahead and get our expressions for the right equation. Again, it's not telling us Kc or Kp, so we're going to look at our states of matter. Here we have gases, so we are going to assume pressure. So remember, with pressure, we are using partial pressure in parentheses. So it is still products over reactants. So we're going to have the pressure of NH3 raised to the power of the coefficient, which is 2. And then we have 2 reactants, N2 and H2. And remember, we are only calculating for Kp if we know that those pressure values are at equilibrium. And then if we are given partial pressures of our substances where we do not know if it's at equilibrium or not, then we are plugging it into Qp, which is going to be the same expression. Right, so here it says write the equilibrium constant expression for the following system at equilibrium. So because it said at equilibrium, I know I'm solving for K, not Q. And I also have gases, which means I'm going to be solving for pressure since it did not specifically tell me. So I have my products first. I have the partial pressure of CO2 raised to the 3rd power, the partial pressure of water raised to the 4th power. Then I have the partial pressure of C3H8 and the partial pressure of O2 raised to the 5th power. And that is my expression. The decomposition of solid calcium carbonate produces solid calcium oxide and carbon dioxide gas. Write and balance the equation, then write a reaction quotient. So first we need to get our equation and balance it. So calcium is a group 2 metal, so it's going to have a positive 2 charge. Carbonate is a polyatomic ion, CO3 minus. So since their charges balance out, it's just going to be one of each, CaCO3. That is going to be solid. And then it's a decomposition reaction, so we only have one reactant. Then we have our first product, which is calcium, again, positive 2 charge, and oxygen, negative 2 charge. So those are going to balance out, CaO, and it says it is a solid. And then it says carbon dioxide gas, so CO2 gas. Now it says write and balance the equation, then write a reaction quotient. So I want you to be very careful when you have questions like this. As you can see, we have 2 solids, which are not considered in equilibrium expressions. So when we write out Kp, because we have a gas and we were not told, all we have is a single product. So it's just going to be the partial pressure of CO2, and since it has a coefficient of 1, we do not need to raise it to any power. So if we are also going to write a reaction quotient, remember these are exactly the same, they're just different values. So if we were to write the expression, it would be Qp with the same mathematical equation. All right, so here we have an equilibrium equation. It gave us the equilibrium constant for concentration at 0.0142. And then it gave us concentrations of all three substances, and it's asking us which way will the reaction progress to reach equilibrium. So clearly we are doing a Q versus K situation here, and our first step is going to be solving for Q. And we know it is concentration. Two reasons. One, we are given concentration values. The other one, we are given Kc. So we are solving for Qc. So first, with the expression, we have our products over reactants, and they're raised to the power of the coefficient. So we have NO squared times Br2, and then on the bottom we have NOBr squared. So now we can go ahead and plug in these values. So we have NO is 0.2 squared, Br2 is 0.8, and NOBr is 1 squared. When we plug that into our calculator, we get 0.032 for our QC. So relating Q and K, if I have 0.032 for my Q, and I have for my K 0.0142, I can see that my Q is greater than my K. So if Q is greater than K, that means at this point I have too many products relating to K, which means I need to shift the reaction to the left or towards the reactants. And I know in our last lesson we talked about that number line and visualizing it for K. You can do the same thing with Q. So remember, in our number line, when K was equal to 1, that means we have the same proportion of reactants as we do products. Well, we are given K in this reaction, and we can see that it is about 0.0142. So in relation to this, when we go ahead and plot our Q, we can see it's slightly greater than our K. So it's somewhere around here, 0.032. So since it is more right on the number line, we're going to have to shift left in order to reach equilibrium. All right, so this question states that when heated strongly, calcium carbonate decomposes to produce solid calcium oxide and carbon dioxide gas. A 2-mole sample of calcium carbonate is placed in a 100-liter reaction vessel from which all the air has been evacuated. The vessel is heated to 898 degrees Celsius, at which time the pressure of CO2 in the vessel is at constant at 1 atm. Calculate the number of moles of CO2 present in the vessel at equilibrium. So looking at what values I have for CO2, I know it's in a 100-liter vessel, which is my volume. I also know that it's at 898 degrees Celsius, so if I add 273 to that, I get 1,171 Kelvin, and that is my temperature value. And then finally, I can see that the pressure of CO2 is held at a constant 1 atm, so that is our pressure unit. So looking at these three, I know I can plug it into the ideal gas law in order to solve for N, or moles. So we know that PV equals nRT, and I am solving for N. So N is equal to PV over RT. So if I'm solving for N, my pressure value is 1 atm. My volume value is 100 liters. My R constant, since I'm using pressure, is 0.0821 liters times atmospheres over Kelvin times moles. And then I'm going to multiply that by our temperature, which is 1,171 Kelvin. So as you can see with our units, everything is going to cancel out except for moles. So we're going to be left with moles, which is N. And now in my calculator, I'm just going to do 100 divided by 0.0821 times 1171. And that gives me 1.04016 moles of carbon dioxide. And looking at my sig figs, the 3 that I used all had 3 sig figs, so my final answer for part A is going to be 1.04 moles of CO2. So now solving for B, it says write the equilibrium expression, Kp, for the reaction. So remember, the expression is just products over reactants, and because it's pressure, we're just going to have our gases, and they're going to be in parentheses. So actually there's only one gas in this, and it's a product, so I don't even need this line. So it will just be the partial pressure of CO2, and there's no coefficient, so it's just as is. And now the second part of B says to determine its value at 898 degrees Celsius. Now, because our equilibrium expression is only the partial pressure of CO2, and we were already given the pressure of CO2 at equilibrium, which was 1 atm, that means that we know that our Kp is equal to our pressure of CO2, which is 1 atm. All right, let's move into 7.4. We know that calculating the equilibrium constant allows us to quantitatively describe the position of equilibrium using the data. At equilibrium, the concentrations of solutions or partial pressures of gases are going to remain constant, and those values can be substituted into the equilibrium expression to determine Kc or Kp. And because K reflects the ratio of products to reactants at equilibrium, its magnitude is going to provide some insight into whether a reaction is either reactant favored or product favored, making the calculation of K a really important skill for solving equilibrium problems throughout Unit 7. All right, so when we are working with equilibrium constants, there are a few things that you have to remember. Number one is that K does not have any units. That is because it represents a ratio of product amounts to reactant amounts. Then you have to remember that pure solids and pure liquids are not included in equilibrium expressions because their concentrations remain constant, meaning only aqueous and gases appear in equilibrium expressions. Then you have to remember that Kc values must be in equilibrium molar concentrations, while Kp is going to use equilibrium partial pressures of gases. It is also critical that all values used are measured at equilibrium. Using values from any other part of the reaction is going to result in the reaction quotient Q. And then distinguishing between equilibrium values and non-equilibrium values is really important. So you have to remember the relationship between Q and K and what that means. All right, this says calculate the value of the equilibrium constant Kc for the system shown if 0.1908 moles of CO2, 0.0908 moles of H2, 0.0092 moles of CO, and 0.0092 moles of H2O were present in a 2-liter reaction vessel at equilibrium. So we have been told that we are solving for Kc, even though we are given gases. This is what we are solving for, which means when we are calculating Kc, we need our molar concentrations of all substances. So let's start off with the expression. We have CO as a product and H2O as a product, and then our reactants are CO2 and H2, and there are no coefficients besides 1, so that remains as is. So then we can go ahead and plug in values, but we do not have concentration. We have moles and we have liters. So before we plug them in, we need to divide these mole values by 2 to get concentration. So for our products, they both have the same number of moles. If I take 0.0092 and divide it by 2, I get 0.0046. And then on the bottom, I have CO2, which is going to be 0.1908 divided by 2. And that gives us 0.0954. And then looking at H2, I have 0.0908 moles divided by 2, which gives me 0.0454 for my concentration. And now I can solve for Kc. And then looking at sig figs, I have 4 sig figs, 3 sig figs, 2 sig figs, and 2 sig figs. So my final answer needs to be in 2 sig figs. So Kc is equal to 2.1, and that is my final answer. All right, now let's calculate a Kp. So Kp for our expression is going to be the partial pressure of our products raised to their coefficients over the partial pressures of our reactants. In this case, we only have 1. So now that we have that, we can go ahead and plug in our expression with our values. So for the partial pressure of O2, I have 0.296. For NO2, I have 1.7. And then for N2O5, I have 2. And then looking at sig figs, I have 3, 3, and 3. So my final answer to 3 sig figs is going to be Kp equals 0.618. All right, AlCl3 is shown to dimerize reversibly in the gas phase. The equilibrium is represented below. E says write the expression for the equilibrium constant Kp for this reaction. So these are both gases, so they are both included in the equilibrium expression. Remember, when it's asking for expression, all you do is write the setup. You're not actually plugging any values in. So first off, we're starting what we're solving for, Kp. Since it's pressure, and I'm going to use parentheses, which is the partial pressure of my product, Al2Cl6, raised to the power of the coefficient, which is 1, and then divided by my reactants, which is only 1, the partial pressure of AlCl3, and that is raised to the second power. Now part F says to use the particle level diagram to calculate the value of Kp, and then I'm going to use the total pressure to get my partial pressures of each. So looking at this specific particle diagram, I can see that I have 1, 2, 3 of my products, which is Al2Cl6, and then I have 7, 1, 2, 3, 4, 5, 6, 7 of my reactant AlCl3. So since we have a total of 10 particles, this makes it nice and easy for us. So our product is 30% and our reactant is 70%. So now we're going to take the percentage of our total pressure, So that is 22.1 atm. And for our product, we get a partial pressure of 6.63. And then for our reactant, we get a partial pressure of 15.47. So now that we have our partial pressures, we can go ahead and plug them in to our expression to solve for the answer of F, which is Kp. So first we have our product. Our product is Al2Cl6. So that partial pressure is 6.63 atm. And then our reactant is 15.47, but it is raised to the second power. So we're going to go ahead and plug those values in, and we end up getting 0.0277 for our Kp value. And then to just understand what K means, remember if it is less than 1, that means at equilibrium we have more reactants than products. And if you look at our particle diagram, you can see we clearly have more reactants than we do products. So that does line up. All right, this FRQ says the partial pressures of the gases in the container are monitored at a constant temperature. Part C says at time T8, is the rate of the forward reaction greater than, less than, or equal to the rate of the reverse reaction, and justify your choice. So whenever we're looking for the rate of the forward versus the rate of the reverse, you need to look at the time before the one you're looking at. So if we are looking at time T8, that means we need to look at where we moved between T7 and T8. And as you can see at T7, all of those values are the same, which means if there was no change in our pressures, the rate of the forward is equal to the rate of the reverse, which is the definition of equilibrium. And then part F says, using the data in the table, determine the value of the equilibrium constant Kp for the reaction represented by the equation below. So for our expression, I know it doesn't ask for the expression, but I always suggest writing the expression just to make sure that you are plugging in values correctly with the correct exponents. Now in this one, the exponents are all 1, so that doesn't really help, but in the future, I think it does minimize errors. So for our product, we have the partial pressure of COCl2, and for our reactants, we have the partial pressure of Cl2 and the partial pressure of CO. So plugging those values in, I have 0.6 for my product, and for my reactants, I have 0.4. I end up getting 3.75, but with our number of sig figs, which is 2, our final answer would be Kp is equal to 3.8. All right, it says the diagram above represents the equilibrium between two isomers of C2H2Cl2. And then the table provides data collection in terms of the experiment to determine the equilibrium constant at 490 Kelvin. In a second experiment done at the same temperature, the concentration of Z at equilibrium is equal to 1 molar. Which of the following is the approximate equilibrium concentration of Y in the second experiment, and why? So we know at equilibrium, our concentration of Y is 1.2 and our concentration of Z is 0.8. Now it's saying it's doing a second experiment at the same temperature. So if the temperature is the same, then the ratio of concentrations between Y and Z is going to be the same no matter what concentration values you have. So what this means is the concentration of products to reactants is going to be the same. So the concentration of Z at trial 1 over the concentration of Y at trial 1 is going to be equal to the concentration of Z at trial 2 over the concentration of Y in trial 2. So we are solving for the concentration of Y in the second experiment. So if I wanted to solve for that, I'm going to have concentration of Y at experiment 1 times concentration of Z at experiment 2 divided by concentration of Z at experiment 1. And that is going to give me a concentration of 1.5, and that is our answer. I hope this video helped. If you have any questions, let me know. I am happy to answer them for you. Have a great day.